welcome to this class. I am Ubani Kirsten and I'm taking you on the subject chemistry. The theme of this lesson is chemistry and environment, and we'll be looking at the topic standard separation techniques for mixtures, part 1. Now, by the end of this lesson, you should be able to distinguish between the physical and chemical properties of matter, distinguish between the physical and chemical changes that matter undergoes, state and explain the classes of matter, state the criteria for purity of a substance, and test for purity of a substance. Now, matter is anything that has mass and occupies space. So anything at all that has a mass and can occupy space. For example, you as a human being, you have mass, right? You have weight. You can occupy a particular space. Where you stand, no other person can stand there because you're occupying that space, right? Your matter. The clothes you wear, you can just look around you and you just identify anything at all that has mass and can occupy space, okay? That is matter. We can also use the name substances for matter. Though it goes beyond substances, it could be human beings and all that. Now, matter exists in 4 forms, basically, okay? There are other forms, anyway, that scientists have proven that matter can also exist, but the 4 basic forms that matter exists are in the solid state, liquid state, gaseous state, and plasma state, all right? Solid, we have examples like ice, wood, metal, anything that has a definite shape. All right. Liquid state of matter, we have examples such as water, milk, soft drinks. Gaseous state, we have things like steam, air, carbon dioxide, methane. These are all gases. Of course, we know that air is what? A mixture of gases, and air has weight and it can occupy space. How do we know that? If you get a balloon and weigh it without air, by the time you blow air into it and weigh it again, you see that the weight of that balloon has changed. And if you want to know the exact weight of the air you've blown into that balloon, all you need to do is what? Subtract the initial weight of the balloon itself from what? The final weight of that balloon. Whatever you get is the weight of air that you have blown into that balloon. So air is a gas, and what? It has weight, it occupies space, along with other gases like carbon dioxide, methane, steam. And we also have the plasma state of matter. Okay, this one is found in sun and what? In stars. Now, matter can change from one given state to another, all right? So this tells us that matter undergoes changes, all right? For example, water can exist in the solid as ice, that is the solid state of matter. It can melt into liquid, and that will be the liquid state of matter. It can also vaporize into steam, and that will be the what? Gaseous state of matter. So you see that some substances can exist in more than one form, as we have shown with water, while some other substances can just exist in one form of matter. But at any given point, a substance must assume only one state of matter. It could be solid, liquid, gaseous, or the plasma state. Now, all substances exist in one state of matter or another. Now, we'll say that we can actually use the term substance when we are talking about what? Matter. Now, let us look at the properties of matter. We are simply saying maybe features, characteristics, the things that make something what it is. Okay? If you look at maybe 2 individuals, you can look at this one and say, oh, he's a fair, tall guy. And you can look at another lady and you say, oh, she's a dark, beautiful lady. These are what? Like features of what? These individuals. So when we talk about the properties of matter, we are looking at what? The features of substances. All right? Now, we can identify a substance by the features it possesses. All right? The water you have there and maybe the plate of eba you have, you can identify them separately in their separate states because of what? The physical things you can see, the physical properties, the features that they possess. All right? Now, for example, salt is white in color. That is something you can easily see. It's a feature of salt. All right? It dissolves in water to form salt water. Another substance, aluminium, is silvery white in color. all right? It can be magnetized and it can conduct heat and electricity. So you see the different features of these two substances we've outlined here. Salt and what? Aluminum. These things we've outlined here as what they possess: color, salt being white in color and it can dissolve in water, and aluminum being silvery white in color and being able to magnetize and conduct heat and electricity. These are what? Features of what? These substances. Now, these features that different substances possess are called their properties. Okay? So these features, whatever feature that you can use to identify a particular substance and tell it apart from another substance, okay? Those features are known as what? The properties of the substances. Now, the properties of matter are of two kinds. We have physical properties and chemical properties. So you can see a substance, you should be able to what? Identify its physical properties and what? Its chemical properties. Now, let us look at some of those properties that we can call physical and the properties that we can call chemical. Now, what are physical properties? The physical properties of matter are those properties associated with the physical changes that substances undergo. They are the features of a substance that can be observed by the five senses or measured without changing the chemical structure of the substance. The physical properties of a substance, okay, are those properties that we can easily look at that substance and know what it is. We can smell it, we can taste, we can even hear, maybe there's a particular sound that substance makes, and we can feel. Okay, and it also tells us that the physical properties of a substance are those features or characteristics we can see in a substance without changing the chemical structure of that substance. That substance doesn't need to undergo any chemical change for us to see what it is made up of physically. Okay, so some of the physical properties of substances are their boiling point, density, melting point, freezing point, hardness, malleability, ductility, color, odor, feel, taste. Okay, so these are just some physical properties that we can actually identify for substances. Now, when we talked about aluminium, say that it is silvery white. When looking at this image of aluminium, all right, it doesn't need to change from aluminium into something else for me to know that it is silvery white in color. I don't need this glass of water to change from water to another thing for me to say that, oh, it is colorless, okay? And if I actually have it here, I can smell it and say, oh, it is odorless. All right? So any property of a substance that we can tell with our eyes, we can tell the color of something, we can smell and know its odor, fragrance or aroma, we can feel it to know if it's crystalline or amorphous, if it is rough or smooth to feel. We can taste it to say, oh, this has a bitter taste or a sweet taste, okay? We can use all these to talk about the physical properties of a substance. When we talk about malleability and ductility, we'll be looking at metals, all right? Some physical properties of metals. They are malleable, they are ductile. But the most important thing here is that what? These are all physical properties. They are features of a substance that we can tell without changing the chemical structure of that substance. For example, water. The physical properties of pure water is that it is what? It is colorless, it is odorless, it is tasteless, it has a boiling point of 100 degrees Celsius and a melting point of 0 degrees Celsius. So all these features can be observed without changing the substance from what it is. Okay? For example, when ice melts, it's still water. What has happened? It just changed from one physical state to another. It just changed from being a solid to what? A liquid. When it also vaporizes, it just changes its state. But that doesn't mean that that substance, water, has changed from being water. So those kind of physical properties we can note about a substance without changing them from what they are called physical properties. Now let us look at chemical properties. Chemical properties of a substance are like the opposite of the physical properties. Okay, the chemical properties of matter are those properties associated with matter undergoing change from one form to another, usually in what? A chemical reaction, which leads to the formation of what? New substances. So we've seen the difference here now. In physical properties, we can observe them without changing that substance from what it is. But for chemical properties, there is what? A chemical reaction that substance has to undergo for us to see its chemical properties. And when that happens, a new substance is formed. So in identifying the chemical properties of a substance, we should know that the internal structure of the substance must be affected. Okay? Using wood as an example now. When it is burnt, its internal makeup is changed by the application of heat until it becomes an entirely new compound, which is what? Charcoal. When you bring firewood and burn it, it changes to charcoal. That charcoal can never be transformed back to what it used to be. And that change means that what? An entirely new compound has been formed, right? And it also means that the internal structure of wood was affected, and that is why it caused the production of an entirely new substance. So for the chemical properties of matter, their internal structures are affected. We can see some chemical properties here, such as fermentation, frying, and burning or combustion. So some chemical properties are rusting, okay? For example, when iron rusts, it will never go back to what it used to be. That iron has been changed to what? Iron oxide. Fermentation of wine, okay? When fermentation occurs, it's a chemical reaction that affects the internal makeup of the substance undergoing that fermentation, all right? Decomposition reaction, for example, when your food decays, what has happened? It's a chemical process. That food that has decayed can never go back to what it used to be before. So these are different chemical properties. So when a substance undergoes these changes, okay, we can use some of these changes to tell their chemical properties. But those other features that we can just observe without affecting the internal structure of the substances, those ones are known as their physical properties. Matter can undergo change from one form to another, and these changes are classified into physical change and chemical change. So now we've known what physical properties are and what chemical properties are. Now let us look at the changes that matter can also undergo, and we've also grouped them into physical changes and chemical changes. So when matter undergoes a particular change, when do we call it a physical change and when do we call it a chemical change? Now let us look at what physical change of matter is. A physical change of matter is defined as a change which can be easily reversed, all right, and in which no new substances are formed. So these two are the criterion for knowing what a physical change of matter is. The first thing is that what? It can be reversed. So if A and B come together to form AB, all right, this AB should be able to form back A and B. If it is not able to do that, it is not a physical change. But if it is able to be reversed, then it's a physical change. Another criterion is that what? No new substances should be formed at the end of a physical change. It will still be the substances that formed that product. For example, water and salt, okay? When you bring water and you add salt into it to form a salt solution, this is just still salt and water, okay? Nothing new has been added, no new substance has come in, and nothing has been removed. It is still the same salt and water. This kind of change is what? A physical change. This kind of change can be reversed. We can reverse it to get back the salt and water. All we need to do is to apply heat on the salt solution, okay, and maybe cause the water vapor that goes off to condense into another container. So we can recover our water back, and when the initial container that you're heating dries up, we'll still have our salt. So we can recover the water and the salt that started this reaction. So we can see that it is reversible, all right? And there was no new change. There was no formation of any new substance. So such a change is known as what? A physical change. And that is why we say that what? It is also a temporary change that does not affect the internal structure of the substance that undergoes the change. The internal structure of the compounds are not affected. It is still water and it is still salt. When they are recovered, we'll still have our salt and we'll still have our water. All right? So their internal structures are still intact. All right? Now, examples of physical change are melting. For example, when a particular substance melts from the solid to the liquid, it's just a physical change. It has not changed from what it is to another. All right? Freezing, evaporation, sublimation, and distillation, amongst others. These are all examples of physical changes that substances undergo that does not change their internal makeup. Now, let us look at what a chemical change is. From what we've seen about physical changes, we now know that chemical changes are what? The reverse of what? A physical change. A chemical change is defined as a change which is not reversible. You cannot reverse a chemical change. And it involves the formation of one or more new substances. Remember the example of wood we gave. It's actually a chemical change because new substance has been formed. The wood has gone from being a wood to being what? A charcoal. Okay? And it is not reversible. You cannot get that wood from the charcoal again. You cannot reverse that reaction. Okay? So a chemical change involves these two. One, the change is not reversible. All right? And the second one is that what? It involves the formation of one or more new substances. Something new must be formed in a chemical change. So a chemical change, we say, affects the internal structure of the substance undergoing the change. All right? That wood that became charcoal, the internal makeup of that wood was affected, and that was why it changed so much so that a new substance was formed. So in chemical changes, the internal structure of the substance undergoing it is what? Changed. For example, we've talked about boiling of firewood. Other examples are the rusting of iron, fermentation of substances, decay of substances, slaking of lime. You can see here, this is a fermentation of wine. The substances that led to this fermentation process can never be recovered from it. For example, you are to prepare egg for your father and you decide to fry it. And when you present it to him, he says, oh, he would have preferred it boiled. At that point, you will not be able to do anything about it because it's already fried. You can't get back that raw egg that you had for you to go and boil it. So that frying is a chemical change that has happened to that egg. Okay, so that's just about physical and chemical changes of matter. Now let us look at what pure substances and mixtures are. When we have a particular substance, when do we call that substance pure? Okay? And when do we call another substance that we have impure or maybe a mixture? All right? Now let us see the difference between these two classes of matter. So what's a pure substance? A pure substance is a substance that has a constant composition which cannot change. This means that substances in their pure form are made up of the same materials throughout, and all their particles are of the same properties. For example, we have water, okay? I like to use water as an example because it's something that we all can relate with. Water is a substance that has this as its composition, H2O, okay? Water with this composition can never change. And we can say that what is a pure substance. Any substance at all that has a constant composition or a fixed composition that can never change. Now, this composition of water can never change regardless of anywhere you find water in the world or in any environment you see it. Okay? Water remains water. If this composition were to change, it will no longer be water. All right? So any substance that has a fixed or constant composition that cannot change, then we can see that that substance is what? A pure substance. Okay? Let's take for example this compound, ammonia. Ammonia will remain one nitrogen with 3 atoms of hydrogen, and this composition will never change for ammonia. When you see something different, that wouldn't be ammonia anymore, but another substance. Now, substances are called pure because they cannot be further separated or broken down into other substances by any physical method. You cannot separate pure substances by physical methods such as filtration, sublimation, evaporation, and others. But there are some chemical methods that you can use to separate them into their respective elements. For example, we have here carbon. Okay, these are elemental pure substances, okay, which we are also going to see. All right. Now, pure substances are divided into 2. We have elements and compounds. We are saying, okay, we have substances that are regarded as pure in their elemental forms, and we also have substances that are regarded as pure even if they are what? Compounds. Now, let us see the difference between them. An element is a substance that exists naturally in the pure form or has been synthesized in the laboratory, which cannot be further separated into simpler substances by any known physical or chemical method. So any substance at all that exists naturally in its pure form and which cannot be further separated into simpler substances by any physical or chemical method is an element. Elements are the building blocks of life. And when you hear elements here, we are actually talking about the 118 known elements, okay, of the periodic table, okay. Examples are helium, lithium, scandium, beryllium, carbon, nitrogen, and other elements. These elements are the building blocks of life. For example, if you pick carbon, you cannot further separate it into any other kind of substance. Carbon is carbon in its pure form. Okay, hydrogen, oxygen, magnesium, these are all substances in their elemental forms. They cannot be further separated by any physical or chemical method. There are 118 of them, okay, as seen in the periodic table. Remember, we said that they exist naturally, or some of them has been synthesized in the laboratory. From the periodic table, elements 1 to 94, all right, exist naturally, okay? Although some of them were synthesized first in the laboratories before they were now finally discovered in their natural forms. But from elements 95 to 118, these elements were actually synthesized in the lab. So when you think of elements, just remember the periodic table of elements, all right? These are the substances that we are talking about. So each element is unique as no two has the same properties, all right? Carbon has different properties from hydrogen, which also has different properties from magnesium, all right? Which also has different properties from tin, and the list goes on and on. This is because of what? Those subparticles they possess that really make them unique. Those subparticles are the electrons, the protons, and the neutrons, okay? Each substance, each of these elements have a certain number of protons and electrons that is different from another element. For example, let's just use 2 elements, nitrogen and oxygen. Nitrogen has 7 protons, oxygen has 8 protons. This number of protons can never change for nitrogen, and this is what makes it what it is, nitrogen. Likewise, oxygen, this number of protons will never change. If it's to change, then it will no longer be this oxygen, to be another element. So, elements are unique because of this reason, all right? Their number of protons, neutrons, and electrons are unique. Example of some elements, okay, are oxygen, nitrogen, magnesium, aluminum, and every other element we can find on the periodic table. Now, compounds. What are compounds? Remember, we are talking about pure substances. We say that they are categorized into elements and compounds. A compound is a substance that is made up of two or more elements in a fixed ratio that is chemically combined. All right? So this tells us that two elements can come together to form a compound, just as when hydrogen combines with oxygen to give us water. Okay? These are two elements, all right, hydrogen and oxygen, combining to give us water. So that is one thing. Then another thing to note about compound is that what? This combination is in a fixed ratio, all right? So it's not just about two elements combining, but they are combining what? In a fixed ratio. You can see that 2 moles of hydrogen is combining with 1 mole of oxygen to give 2 moles of water. And this composition of water, H2O, is fixed. It can never change, all right? For every time you think of the chemical formula of water, it will always be 2 hydrogen atoms combined with 1 oxygen atom. So this is what? A compound. So water has a ratio of 2 hydrogen atoms to 1 oxygen atom. This ratio cannot be changed no matter what. Now, when elements combine to form a compound, a new compound with entirely different properties from the reacting element is formed. So we had this hydrogen combining with oxygen to form water. You see that the new compound, water, is going to have properties that are very distinct and different from the reacting elements that formed it. Okay? When you list the properties of water, okay, it has no connection to the properties of either hydrogen or oxygen. So they are what? Chemically combined. This hydrogen is chemically combined to oxygen to give us water. So that is how we can differentiate compound from perhaps a mixture, all right? Because as we go on, we will see what makes a mixture different from a compound. Substances that are regarded as compounds are what? In a fixed ratio, okay? And they are usually chemically combined, all right? So this is actually what makes them different from mixtures, and we're going to look at what mixtures are. Now, elements that make up a compound cannot be separated by what? A physical method. No physical method can be used to separate, for example, water or ammonia. You cannot use any physical method of, say, filtration or evaporation or sublimation to separate these elements that make up these compounds. Okay, but there are some chemical methods available that can be used to separate them into their respective elements. Also, the component elements of a compound are always present in a fixed ratio by mass. Of course, we have said that for you to call this water, okay, it has what? A fixed composition. For you to call this water molecule a compound, it means that it has a fixed composition that cannot change, all right? This compound, ammonia, also is present in a fixed composition that cannot change. These are all examples of pure compounds. Other examples are carbon dioxide, carbon monoxide, sucrose, hydrogen peroxide, sodium chloride, ethanol. As you can see from these examples, they have specific number of elements that what make them up. For example, sucrose has 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. This is what makes it sucrose. If this number of elements change, it will no longer be sucrose. Ethanol has 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. They must be present in this particular ratio. And this is what makes them compounds. They can also not be separated by what? Physical methods, but there are chemical methods that we can use to separate them. Now let us look at mixtures. A mixture is any substance made up of 2 or more constituents with indefinite composition that can be separated by a physical method. Now these constituents could be elements, compounds, or both. So we are saying that qualities that can make a substance a mixture is 1, the different constituents of the substance has to be present in an indefinite composition. Remember that for compounds, we say they have to have a definite what? composition. But for mixtures, the different constituents that make it up are present in what? An indefinite composition. There is no particular composition. You can find that particular substance in this composition today, maybe 10% this way. Let's say a substance that has two constituents making it up. This side is 10% and this side is 30%. All right? You can still find this same substance in maybe another environment, and you would have one constituent as 20 and the other constituent as 20. So there is no definite composition of the constituents that make up a mixture. All right? And mixtures too can be separated by a physical method. We can use any of the physical methods available, okay? Of course, the appropriate physical method to separate mixtures. And these constants we are talking about could be elements, they could be compounds, all right? So we can have two elements coming together to form a mixture. We can also have an element and a compound coming to form a mixture. But remember, if it's a mixture, then it doesn't have a definite composition of those elements. Those elements can appear in whatever amount they choose to appear in that substance. Now, substances that make up a mixture retain their original identity and properties. Okay? Examples of mixtures are air, urine, sand, oil in water, salt or sugar water solution, fruit drinks, palm wine, milk, and so on and so forth. For example, if we take air, we say that air is a mixture of gases, right? Already we call it a mixture. The gases that make up air can be separated into their various components, all right? We can separate oxygen from air, we can separate nitrogen from air. So it means that what? They have retained their original identity. That is why we can actually separate them. Likewise, things like urine, sand, oil in water, sugar in water, blood, there are different physical methods that we can use to separate these substances. And because they can be separated into their constituent substances that make them up, they are what? Mixtures. Remember that compounds cannot be separated again by any known physical method. Elements cannot even be separated by any known physical or chemical method. But for mixtures, we say that they can be separated by what? Physical methods. Now, mixtures can be solid in liquid. For example, when sugar is dissolved in water. Sugar is a solid and water is a liquid. So, a mixture can be solid in liquid. It can also be gas in gas. For example, when we talked about being able to separate oxygen from air. Oxygen is a gas that is dissolved in another gas, a mixture of what? Gases known as air, all right? So, it could be gas in gas. It could also be solid in solid. For example, tin and copper. Alloys most times are what? Two solids that are combined together. So, we have solid and solid. So, mixtures can take any of these forms. Mixtures are divided into two types, okay? And this is based on the uniformity or distribution of particles. So we have homogeneous mixtures and heterogeneous mixtures. Remember, mixtures, whether homogeneous or heterogeneous, can be separated by physical methods. Let's see what homogeneous mixtures are. A homogeneous mixture is a mixture made up of particles that are evenly distributed throughout so that all regions of the mixture have the same properties, okay? So when we have a mixture, all right, that has the constituents, the particles that make it up, well distributed, uniformly distributed in that mixture, then we can say that that mixture is a homogeneous mixture. Take, for instance, the salt water solution, okay? That is an example of a homogeneous mixture. That kind of mixture can see that if you were to take a part of it, maybe from the top, and take a part of it from the bottom, you will see that it's going to give you the same taste because the particles of the salt are evenly distributed in the water. So such mixture is what we call a homogeneous mixture. We say that the individual particles are well blended into each other so that they cannot be differentiated from each other. So if you have a salt water solution, can you differentiate the salt from the water? That's not possible. You will just see one form, the salt water solution. So you will not be able to tell the individual particles and say, oh, this is water particles and this is salt. All right? So that is a homogeneous mixture. Are well distributed. They are evenly distributed. And that is where we can use something like this to talk about a homogeneous mixture. All right? So in this container, we have two particles making up this substance. We have the purple particle and the green particle. And you can see how uniformly distributed they are in this container. We can see that we have the purple particles in all regions of the container. We also have the green particles in all regions of the container. This kind of uniform distribution is what we call homogeneous. All right? A homogeneous mixture can also be called a solution. So examples of homogeneous mixtures are given here. For example, some food we eat, like chocolate, coffee, milkshake, orange juice, even our paints, can see that these substances, you can't tell the individual particles that make them up. You can't look at them and say, oh, this is this and this is that. Okay? They are all well blended into each other. So a heterogeneous mixture is the opposite of what? A homogeneous mixture. This is a mixture that is made up of particles that are not evenly distributed. Some regions may have different properties from others. For example, oil in water. Okay? When we have something like this, oil in water, you can see that at the top we have more of the water particles, and most parts of the container we have water particles, and then we also have some of the oil particles just in some regions of this container. We don't have it in all the regions. And you can also tell the substances apart. You can see the oil droplets and the ones on top of the container. You can see that, oh, this is oil, and this other side of the container is water. You can even tell that there are up to 3 substances that are in this container. Here is one substance, here is another substance, and here is another substance. You see that they are not well blended into each other, and you can tell them apart. You can tell the substances that make up such mixtures apart. Now, the individual particles are not evenly or uniformly mixed, okay? They can be easily seen with the eyes. They can also be easily separated by physical method, and they can contain more than one phase. Just like the example we talked about here, you can see that this contains like 3 phases. We have phase 1, have phase 2, and we have phase 3 of this mixture. We have a drink here, this an ice cream. Okay, you can see that it has several phases making it up. Mixtures such as suspensions, colloids, and emulsion are heterogeneous. At a glance, we see the different classes of matter. We say that what? We have the pure substances and the mixtures. Now, the pure substances are further divided into elements and compounds. All right? Remember what we said about elements? Elements cannot be further broken down into any other substance again. They are the building blocks of life. Compounds, we say they are made of what? 2 or more elements that are what? In a fixed ratio that cannot be physically separated. Then we looked at mixtures. We said that mixtures are also of 2 types, which are the homogeneous mixtures and the heterogeneous mixtures. And we said that the homogeneous mixtures are the ones that the particles that make up such a mixture are evenly distributed, and they cannot be told apart. And we have an example such as maybe a cup of coffee or a cup of tea. All right? Then we have heterogeneous mixtures. We say that it's a mixture that the particles are not evenly distributed and they can be told apart. You can see an example here is what? Oil and water. can see that the oil, which is of course lighter, is at the top of this container, and the water, which is a substance, is at the bottom of the container. So here is a table showing us at a glance the difference between pure and impure substances. Impure substances here, we are actually referring to what? Mixtures. So we see that pure substances have a constant composition which cannot change, all right? And we say that mixtures are made up of substances with varying composition. Whatever they are made of in mixtures, the components of a mixture are not what? Definite. They can change depending on different factors. 2. Pure substances are made of particles that are chemically bonded. Mixtures, on the other hand, are made of particles that are not chemically bonded together. Another difference is that pure substances cannot be separated by any physical method of separation, all right? Because they are chemically bonded. They cannot be separated by any physical method. But mixtures can be separated by what? Physical methods of separation, because they are not chemically bonded. Materials in a pure substance, usually compounds, do not retain their original identity, okay? While for mixtures, each material in a mixture maintains its original identity, and that is why they can be separated by physical methods. Okay, so in our next lesson, we'll be looking at the various physical methods that we can use to separate mixtures. Now, we're looking at tests for purity of a substance. We've been talking about pure substances and mixtures. So when we have a substance that we say is pure, how do we test for its purity to really know that it's a pure substance? Now, to determine if a substance is pure, that is, if it has a constant composition, or if it is impure, that is, it has varying composition, we can use either of these methods. Okay, so the two methods that are available are melting and boiling point of the pure substance and paper chromatography. So let's see how we can use melting or boiling point and paper chromatography to determine the purity of a substance. Melting or boiling point of the pure substance. Now, every given pure substance has a melting point and a boiling point that is fixed at a particular temperature. For example, water has a boiling point of 100 degrees Celsius. Okay? Now, the boiling point of water is fixed at this temperature. Pure water. The boiling point of pure water is fixed at this temperature. Now, to assess the purity of a substance, we determine its melting point if it's a solid substance, or its boiling point if it's a liquid substance. So if the substance we have that we want to know its purity is a solid substance, we check for its purity by determining its melting point. But if that substance is a liquid, we test for its purity by determining its boiling point. If there are impurities in that substance, the temperature will be affected, all right? That particular temperature at which that substance is supposed to boil or melt will be affected by the presence of an impurity. Now, the presence of impurities in a solid substance will reduce its melting point, while the presence of impurities in a liquid substance will increase its boiling point. For example, if you have gold, okay, gold melts at 1094 degrees Celsius, okay? It's a solid, all right? And then we have water, of course, that boils at 100 degrees Celsius. Let's give the example with the solid first. If we have impurities in gold, all right, this melting point will be reduced. So by the time we test for its melting point, we may realize that it will melt, say, maybe at 900 degrees Celsius. So when we are testing for the purity of this substance, gold, and instead of melting at 1094 degrees Celsius, it melts at 900 degrees Celsius. It tells us that there are impurities present in that gold. All right? So the presence of impurities reduces the melting point of substances. But if it's a liquid substance, such as liquid water, that boils at 100 degrees Celsius, and in the course of boiling, we realize that the water boils at maybe 120 degrees Celsius. It means that it has boiled at a temperature that is higher than its normal boiling point, right? So it tells us that there are impurities in that water that has made the boiling point to increase to 120. So it is not pure water. And the gold as well is not pure gold if it melts at 900 degrees Celsius. So this is how we can use melting point and boiling point of substances to tell if they are pure or not. So if a substance is pure, okay, the measured value will agree with or be the same with the given data for that substance. The given data for the boiling point of water is what? 100 degrees Celsius. Water will be called pure, all right? If what? If at the end of testing for its boiling point, okay, the measured value, that value we get, okay, when we are measuring that water, the value we get, if it tallies with the given value for the boiling point of water, then it means that that water is pure. But if it does not tally with the given data, all right, it means that what? That water is not pure. Every substance, all right, every pure substance has a particular melting and boiling point. And because they have particular melting and boiling points, when we use this method, we can actually tell if there are impurities in that substance. So this is the criterion that we can use to determine the purity of a given substance, okay? If the one you measure tallies with the given data for that substance, then that substance is pure. But if it does not tally with the given data, it means that that substance has some impurities in it. Now, this knowledge, all right, that impurities generally lower the melting point of solids and increase the boiling point of liquids, is actually employed in some countries where, for example, the temperature falls below 0 degrees Celsius. For instance, salt is used as an impurity. It is introduced on icy roads to de-ice them, that is, to melt the ice. When you have pure water in the form of ice, all right, whatever you introduce into it, such as salt, that thing is now what? An impurity, okay? And we say that solids, the impurity reduces what? Their melting point. So if that ice, of course, is water now, if it's supposed to melt at 0 degrees Celsius, it may now be melting at, say, minus maybe 0.08 degrees Celsius, okay? This is a lower temperature compared to 0 degrees Celsius. So this knowledge, you can use it to de-ice roads. So countries that have heavy ice on the roads, maybe due to snow formation, they can actually introduce salt on the roads to lower the melting point of that ice so that it will melt faster. So when they do that, they are preventing roads from becoming too slippery and also making them safe for vehicles to travel on. Now let us look at how paper chromatography can be used to test for the purity of a substance. Now, we'll be talking more on paper chromatography in our next lesson when we'll be treating the various physical methods that are used to separate mixtures. But this paper chromatography simply makes use of two phases, a mobile phase and a stationary phase, all right? But basically, how we can use it to determine the purity of a substance is that a pure substance, okay, when tested with what? This method, paper chromatography, a pure substance will give just one spot on what? The paper. For example, this is just a mixture. This is an ink, okay? We have an ink placed on this spot, all right? By the time the mobile phase moves along the stationary phase, the different components, the different substances that make up this ink separate so that we can tell them apart, all right? But we are saying that if the substance is actually pure, it is not going to give us different spots like we have with this ink, but it will just give us one spot signifying just the presence of one substance. So if it gives us more than one spot, if it's a substance we are trying to test for its purity and realize that, oh, on this paper chromatograph, we are having more than one spot, then it means that there is another substance that is present in that substance. And that other substance is the impurity. But if it only gives us one dot on the paper, then it means that it is just the substance we are talking about. No other substance is included in it. We can use this method to check the purity of colored substances such as dyes, pigments, and food samples. So we can use this paper chromatography method to check for the purity of different colored substances. That's not to say that we cannot use paper chromatography to test for colorless substances. So with this, we have come to the end of this lesson, okay? Now, we'll take a quick summary. We said that physical properties of matter are those properties associated with the physical changes that substances undergo. We said that chemical properties are those properties associated with matter undergoing change from one form to another. Then we looked at the physical and chemical changes of matter. Physical change of matter is defined as a change which can be easily reversed, in which no new substances are formed. Chemical change of matter is defined as a change which is not reversible and involves the formation of one or more new substances. We say that pure substances are substances that have a constant composition which cannot change. We also looked at what a mixture is. A mixture is any substance made up of two or more constituents with indefinite composition that can be separated by a physical method. Now we say that the purity of a substance can be determined by two methods: the melting or boiling point of the pure substance and paper chromatography. Now we'll take a quick test. Which of the following are the two broad classifications of matter? A, compounds and mixtures. B, elements and compounds. C, pure substances and mixtures. Our answer is not A, neither is it B. Our answer is C. We say that matter is classified into pure substances and mixtures. Which of the following methods can be used to test for the purity of a substance? A, physical method. B, fractional distillation. C, paper chromatography. Well, our answer is C. We say that the two methods used to test for the purity of a substance is 1, the melting or boiling point of the pure substance, or by paper chromatography. Thank you for staying with me. I'll see you again.
If you enjoyed this video, hit the like button, drop a comment, and subscribe to our channel. You can also turn on notifications to stay updated on new videos on this channel. This BrainFriend video was brought to you by Synforest. For more of these amazing e-learning videos, get your copy of BrainFriend. With more than 1,000 e-learning videos, over 74,000 test items in more than 40 subjects, a career counseling guide, and many other amazing features, BrainFriend remains your foremost e-learning and exam preparatory software. BrainFriend. Learn better, make excellent grades.